All right. So, so in this video, we're going to define what shear strain is. So if we have our stress element, all right, and we apply a shear strain stress to that element, all right, so we'll call this stress tau xy, all right, and what will happen is due to that stress, the stress element would deform. So in 3D, it looks like this. In 2D, that stress looks like this. All right, and that stress causes the system to deform. All right, so we can define shear strain as by the change in the angle BAD. So here's our angle BAD. All right, and then here's our new angle B prime A prime D prime. Okay, so we can say that gamma xy, which is our shear strain, is going to be equal to the negative of that change in the angle BAD. Okay, so the change in the angle is going to be the final angle minus the original angle, so it'll be angle B prime A prime D prime minus angle BAD. So what this ends up being is actually just the original angle BAD minus the new angle B prime A prime D prime. All right. So once we have the uh, once we have these angles, we can then calculate the shear stress using the shear modulus. So we can relate gamma xy to tau xy using the shear modulus. So we can say that gamma xy is going to be equal to tau xy divided by g, where g is equal to the elastic modulus times 2 plus 1 plus the Poisson's ratio. Right? And in a similar fashion for the other shear strains, um, uh, gamma yz and gamma zx, those are going to just be equal to tau yz over g, and tau gamma zex is going to be equal to tau zx over g. Now, the one thing to note here is that unlike the normal strains where they have the normal strains are dependent on sigma x, sigma y, and sigma z, the shear strains are independent of the shear, like each other's shear stresses. So tau x, gamma xy is only a function of tau xy, gamma yz is only a function of tau yz, and gamma zx is only a function of tau zx. So that concludes how a definition of shear strain, how you can relate shear strain to shear stress.